Hey class, Adam Ward here. This is the second video in our Open Channel Flow 2 lecture, and this is the one where we're going to focus on rapidly varied flow, and specifically we'll talk about hydraulic jumps and how we can use the toolkit we've been building all semester to analyze them. Alright, so first off, what is a hydraulic jump? Shown at the top of the page is a photograph of a hydraulic jump, and at the bottom is a schematic. And what happens in a hydraulic jump is we're going from supercritical flow on one side, the left side of the screen in this case, to subcritical flow on the right-hand side. And so this is not about an inflow or an outflow of water. It's the same mass flow on the left and the right, but you're seeing the exact same behavior in both the supercritical and the subcritical phases of flow, if you will. So in order to analyze a hydraulic jump, we're going to use this diagram shown on the bottom half of the slide. And I just want to acknowledge here that we're going to work today through about the simplest one-dimensional treatment of a hydraulic jump that's possible. One simplification we'll make, for example, is we will not account for shear stress on the bed. Otherwise, this diagram should look relatively similar to the diagram we used in our analysis of uniform flow. You'll note here that we've got the bed set at horizontal, so there will be no weight force that we need to include if we're analyzing in the X direction. But we still have those hydrostatic forces, F1 and F2. We've got a depth of flow on the left and right, Y1 and Y2 respectively, and similarly a velocity, V1 and V2. In the middle of this hydraulic jump, we have all of this turbulent mixing as indicated by the squiggly lines. And that causes a net head loss. So we're dissipating energy as we flow through the middle of this hydraulic jump. You can see that turbulence visualized in the top part of your slide. And just to remind you, what's happening as you go from left to right in that photograph is you're actually going around that specific energy diagram, passing through the critical point. We know at a critical point, Froude number would be equal to 1, and you would get a standing wave. So these hydraulic jumps are waves, but they don't move as a wave in a lake or at a coastline would. Instead, it appears to just be this sort of standing bit of turbulence. And in the next video, we'll do an example, and I'll show you some additional photographs of hydraulic jumps. Okay, so we're going to use all the tools in our toolkit for the hydraulic jump problems. Conservation of momentum first, and then mass and energy next. So if we write conservation of momentum in the X direction or the horizontal direction, we would end up with this. The sum of the forces must equal the mass rate times velocity out minus velocity in. So let's start to unpack some of the terms we're going to have to deal with here. Now, in terms of hydrostatic forces, we of course remember force on a planar surface is gamma times depth to the centroid hc times the area. And for this problem, we could define the centroid as half of y1, and we'll define the area as y1 multiplied by b, where b is the width in and out of your screen. So we're just envisioning a rectangular channel at the moment. Force 2 can be similarly conceptualized related to depth 2. For our mass rate, that's of course mass per time. We could define that as density times the volumetric flow rate, or density times area times velocity. And we can even plug in for area width multiplied by depth. And so you'll notice I've chosen to plug in y1 v1. You could absolutely plug in y2 v2, and that equation would have to hold as well. Finally, you'll notice that some of these terms have specific weights, some of them have densities. And just a reminder to you that those are not directly interchangeable, but can be converted from one to the other through gravity. So one is mass and one is weight form. And so given all of that, if we make those substitutions and organize ourselves, we end up with the equation that's at the bottom of our page here. y1 squared over 2 minus y2 squared over 2 is equal to v1 y1 divided by gravity multiplied by the difference in velocity magnitudes, v2 minus v1. Whew, all right. So this is about how far we can get from conservation of momentum. It has y1, y2, v1, and v2. And so this tells us that, of course, there is this relationship between depth and velocity at both sides, and the two sides are related to one another. It is highly unlikely that we're going to have all of the information we need here to solve a practical problem, but we can actually continue our analysis by bringing some additional tools to bear. So first, let's consider conservation of mass. The mass rate into our control volume must be equal to the mass rate out of our control volume if we're at a steady state, which we are. So volumetric flow rates must be equal. Put another way, A1 V1 must equal A2 V2. Or we can substitute in channel width B and depths Y1 and Y2. And so that's a pretty convenient way for us to interchange between depths or velocities. And finally, we can bring conservation of energy to bear on the problem. And this will look like a lot of what we did in our first lecture about specific energy, where we were working with the energy equation. For a horizontal problem as this, what we're going to end up with is, on the left-hand side, the pressure head term, or depth of fluid Y2, plus the velocity head is equal to the pressure head at Y1 plus the velocity head at Y1 minus the head loss. And in this problem, as we've defined it so far, that head loss will be due to turbulence. But just as a reminder to you all, if you wanted to include shear stresses, this is one place that they would show up. They would have shown up in your conservation of momentum problem as well, but those shear stresses do represent an energy loss as well as a force, and so you'd have to account for them in this spot. Now, we won't do that, but I wanted you to see where those more complicated solutions might arise. Okay, before we pull this together, just a quick aside. If you were working with uniform flow, you would have y1 equal to y2, v1 equal to v2, and there would be no net loss of energy, right? And so these solutions are extremely simple for uniform flow, and that's what we covered in the previous lecture video. That's not the case for us, so we're going to proceed by pulling together some of these equations. So let's bring it together. One of the things we can do is use the conservation of mass equation to help eliminate V2 from our momentum equation. And so what I've done is just define, I've taken what used to be a V2 that was in this position that I've overscored with orange there, and I've replaced it with an alternative definition. So that's just taking V2 out of the momentum problem. And you can similarly factor some terms out there to try and simplify your problem. Now from there, we can factor out a y1 minus y2 from the left-hand side of the equation. We can divide both sides by y1 minus y2, and we can organize. And if you trust me to do the algebra, you end up with an equation like this. The quantity y2 over y1 squared plus y2 over y1 minus 2 times the Froude number at 0.1 squared. And so you'll remember Froude number, of course, would be V1 over root G Y1. That is our Froude number calculated at 0.1. So we're now able to simplify our momentum equation to this. And if you're looking closely, this is actually a quadratic equation. Right? So if y2 over y1 is what you want to solve for, it's the quadratic equation that can help get you there. So from there, we can plug it into the quadratic formula, we can rearrange it for what we want, and we get a solution that looks like this. This is a useful equation. This is the one I want you to write down and know how to work with. That ratio of depths, y2 divided by y1, is equal to 1/2 times the quantity of -1 plus the square root of 1 plus 8 times the Froude number on the upstream side squared. And just a couple of quick notes on this. If you're doing this as a mathematical solution to the quadratic equation, you would have a plus or a minus. You'd have two roots there. We're only considering the positive root because the negative is not physically possible here. The other note is this is only true in the case where, and I think I've written that wrong. This is only true in the case where the Froude number is, pardon me, in the blue there, I'm changing it to a greater than. If the Froude number upstream is greater than 1, meaning that you are in the supercritical condition upstream of the jump, this works. On the other hand, if you are in the subcritical case on the left-hand side, there isn't a hydraulic jump and this equation is not valid. In other words, you shouldn't use this equation unless you know a hydraulic jump is being described. So that suggests that you should always check the upstream Froude number before you use this equation. It will not work for subcritical flow, for example. This is only true for the supercritical to subcritical transition across a hydraulic jump. Okay, so this is largely using our conservation of mass and momentum equations. If we revisit our energy equation, we can formulate a solution that looks like this beast. It's not particularly pretty in terms of an equation to work with, but what is notable here, and again this only applies if your Froude number is greater than 1 on the upstream side, so if you're in that supercritical condition, this lets you calculate the head loss across a hydraulic jump. So what we've done is combine what we had on the last page with our energy equation. And what we can then do is estimate the head loss due to the turbulent mixing in the middle of that hydraulic jump. Okay, so this video was a lot of mathematical derivation. It was showing us that mass, energy, and momentum conservation can all be applied to hydraulic jumps to make some useful predictions. What I'll do in the next video is actually work through a hydraulic jump problem so you can see how these equations might be used in practice. All right, folks, thanks for sticking with me, and I will see you for the third video momentarily.